Today's guests are Duncan Dickson and Brian Moore. We join their conversation in the faculty lounge.
Consummate mathematician, and I think that's what a lot of young students think. You know, I'm taking calculus because
because I have to, right?
You know, and they make they want me to No, you need to have an understanding of the world around them, so that you can react to it,
right?
And it's the same thing. Why do I have to take history? Well, because you need to know what's going on in the world around you. Not because you're going to be a historian or teach history to anything, but you at least need to be aware.
Exactly.
And I think the same thing with calculus or any of the maths or those things. How does it impact my daily life?
Right.
In that.
I'll share this with my students tomorrow and see if I can.
You teach on Fridays?
I do indeed.
Wow.
Yeah. So
one of the unlucky ones.
I guess so. It's only that one class Friday morning. So.
Friday morning, 3 hours.
No. It's a 4-hour class, so I teach it for an hour and a half, 3 days a week.
3 days a week.
Yeah. It's a good class, though. I read poetry to them, and I try to spice it up with other things.
Make it a little bit interesting. Yeah. Because most of us look at math and go, ugh,
right.
Eyes roll back in your head.
Right.
Yeah. So how do you make math interesting?
Well, see, this is
How'd you get into math? I mean, in high school, were you, I want to be a math geek?
No, that's definitely true. I didn't say that. As I was growing up, I always said I wanted to be a geologist.
Okay.
So
what part of Colorado are you from?
I'm from, just west of Denver. I grew up in Golden? Boulder area.
Coors.
Yeah, that's right. Yeah. I actually went to school in Golden at Colorado School of Mines. So yeah. This is a good place to grow up, but I was always the kid that took my microscope to recess.
Everybody else was playing kickball.
Right. Well, I had another friend that did it with me, though, so it wasn't, I wasn't alone. So, but yeah, back to your question about how I never said all the time I wanted to be in math, and it just it's strange how it works, but there were just certain teachers I had and events that took place that just took me down that road, and I've always liked math, but I guess that's why I ended up where I am. But it's not.
Did you study math undergraduate?
Yeah, I did. Yeah.
Yeah. And then at Colorado School of Mines?
Yeah, actually, I've been in academics my entire life. I've never left. Yeah. I've been doing math for a lot of years now, actually.
How many permutations of these formulas can you do without going bonkers?
It's a good question, actually. I've noticed this recently, that all these movies that come out that have mathematicians in them, they always go crazy, right?
Yeah.
I think that's
it's a beautiful mind.
Right. Well, there are times when I feel like I'm going crazy. If I look at it too long, it's true. I do feel like you have to sometimes you have to step away from a problem to ever solve it. So, there are times when, I look at it so long and I get stuck in the same rut of thinking about the approach I'm taking and why this isn't working. And sometimes you do have to just leave it for a while, think about something else, go on a hike or something, and eventually the solution, the way of going about it will come to you if you leave it. But you can make yourself crazy if you don't leave it. Yeah. So
outside of engineering, which I understand you need a lot of math.
Yeah.
And a lot of the algorithms and that sort of thing to, if we're going to build a bridge and we need to understand the failure factors or, the wind shears on buildings and that sort of thing. Outside of that, what do we need math for?
Oh my goodness. It's,
well, you're talking to a neophyte.
Yeah, I know.
mean, you know,
yeah, you're right.
I'm just a poor old HR guy.
You're right. It's all over the place.
I do adding, subtracting, multiplying, and dividing, but and I can do percentages.
I understand.
But the rest of it is kind of past me.
So let me tell you first about my own research and how it's a little. It's being used in ways that you probably would never imagine. So one of the things that I've been working on for about 4 years now is we have the system of equations, basically.
So you started this at Surrey? Was this your dissertation?
No, I started this at McGill University.
At McGill, okay.
Yeah, it was a postdoc I had there, and so we've got these. It's just equations that tell us how the nervous system works.
Okay.
So basically, there was two guys, Hodgkin and Huxley. They're scientists. They actually won a Nobel Prize for their work. And
in genetics, right?
Yeah, and what they did was they ran some experiments on a giant squid to see how the nervous system worked for this squid. And this was in the early 50s. That's when they published their papers. They won the Nobel Prize in '63 or something. And
I think I remember it.
Okay. Yeah, and so they came up...
You weren't alive, but I remember.
You're right, okay. Okay. So they came up with these equations that tell how the nerve works on this giant squid.
Okay.
And so apparently what happens is your brain sends this electric pulse, and the electric pulse travels through the nerve, and it tells your finger or your eye or your arm or whatever what to do.
So all these synapses.
Yeah, it's just it's electricity basically running from one nervous cell to another. Okay, and so they came up with these equations, and they're really hard to solve. And so it's been 50 years, and people are still studying these things to try and understand how they
came up with them.
Yeah, well, we understand how they came up with it, but they're trying to understand, what do the equations tell us about how it actually works? How does how the nervous system actually works? What is it doing? Why is it doing this? And all these things.
Is this one of those equations that I walk in the room and you've got it all over, 14
well,
whiteboards?
It can fit on 4 lines.
4 lines, okay.
Or 5 lines, maybe. So there's a nice compact way of putting it. There's simplifications of this too, and this is typically what people do, is they say these equations are way too hard for us to solve, so let's maybe think about some simplifications. And it's typically what we do is start with the easy problem and understand that before we move up to the harder one. And so that's what one of the things I've been working on for a few years now is one of these simplifications of the problem to understand how it works. And the particular problem that we've been working on has to do with understanding multiple sclerosis. So if we change parameters in the problem, we can start to see what happens when this electric pulse travels.
So do you work with the physicians?
No, actually I have not actually talked to any physiologists about this problem. There's somebody I work with who does talk with physiologists, and basically he tells me this is an important problem, and I'm a math guy, so it's kind of what you were saying earlier, that it's good to know how to talk to these people, and sometimes it's difficult.
Yeah, because I would think the physician, is got a whole different mindset.
Indeed, yeah.
Than they're trying a mathematics approach to solving MS.
Exactly.
Kind of a difficult, thing to come up with.
Right. Yeah. So what they think happens in MS is there's this insulation around the nerve. It's kind of like your cable that you plug your TV in with. If you pull the insulation away, the electricity won't travel anymore. Right. So this insulation around the nerve starts to get deteriorated by the disease, and then the pulse just can't get through anymore. And so what we've done with these equations is set it up so that there's a place where there's deteriorated nerve, and we try to see what happens when this pulse hits this region. If it stops there, how much deterioration there has to be to make it stop. And
so is the theory you go back and repair that, the conduit, if you will, around the nerve?
Right. If
ultimately.
Well, the whole idea of the study is is to understand the disease. It's to understand how it works. I mean, what we do, I mean, I guess in order to cure the disease or come up with better medications, better medical treatment, you have to understand how it works in the first place. And so that's kind of the idea, is just to understand what is going on in there. So coming up with, you know, rigorous formulas that show this is a really good way to see what's actually happening.
So how do you bring your research down to those freshmen and sophomores that are being forced into your classroom?
That's a great question.
Because I mean, you know, I mean, that's a very noble effort.
Right.
But I'm sure those those 18 and 19-year-olds are a long way from getting there.
Yeah, definitely. So far, I mean, I've only been teaching for a few years now, and I've had a couple of undergraduate assistants that have helped me with this project. So it's taken, you know, me working with them one-on-one for an entire semester, and they are, they're seniors in the math program, and so they have a good grasp of things already. It takes them half a semester to learn the problem, and then another half to contribute a little bit to it, and then
they graduate.
Yeah, exactly.
Yeah.
And so with the students in my classes, the best I've been able to do so far is just share it with them, in the, you know, like I just shared it with you, and then, you know, I could even write out the equation, because they could look at that and understand it in my calculus class, because it's got some terms that they would see and recognize, and they could understand how it's set up that way. But how to solve it, they'd have no idea where to even start. And so I can show it to them and show them that, you know,
they can probably solve for X, but beyond that, they're you know, they're in trouble.
Right.
Yeah.
But yeah, so I can show them what it looks like and why it's important, but I guess it's just to show them that they need calculus to get that far, in a way, you know what I mean?
Yeah.
So, but other than that, I don't know how I could take it farther than that, if it's possible or not. Maybe.
Yeah, there must be days when it's frustrating for you to, you know, finish a class and think, oh my gosh, did I get to them today?
Oh yeah,
you know.
It's true. Yesterday was one of those days.
Was it?
Indeed, yeah, in fact it was. So.
You know, you walk out and rattle your head and say, you know, did they get anything?
Right. You know? Which is kind of difficult, because you know sometimes really this stuff comes pretty natural to me. Otherwise, I wouldn't be doing it in the first place.
This is your talent.
Right. So I kind of see it in a different way than they do in the first place. So for me to understand why they don't see it that way, it can be difficult sometimes. But I do want to make the effort, and I do like it when I do connect with them. It's a great thing.
Do you teach any upper level classes?
Yeah, I'm teaching a scientific computing class, which is a graduate level course right now.
Scientific computing?
Right, yeah. So the basic idea of that class is that they learn how to solve problems on computers.
Okay.
So which can be very challenging. One of the biggest issues in this class is understanding the error, because if I solve it on a computer, I'm getting an approximation, and of my, you know, whatever problem I'm solving, I get an approximation of the solution, and then you can't solve the problem exactly, but the only way to look at the error is to look at your approximation and the exact solution and compare them. And so you have to be really creative with how you figure out what the error in your approximation is in the first place. So there's a whole field of mathematics devoted to understanding how to do this for different problems.
Now, in statistics, you know, you and I were enabled with programs like SPSS that really made statistics a lot easier than, you know, people that got their, you know, doctorates, you know, 25 years ago.
Right.
And, you know, had to do everything, you know, hand calculation, and you know, that all we had to do is plug it in and go, and,
exactly.
You know, it was there for us.
Yeah.
Are there any programs like that in math that you can utilize?
There are several. There's one called Mathematica, and there's one called Maple, which do all the manipulations that you would do in algebra or calculus. They would do those things for you. sometimes worry that my students will actually learn about Mathematica before they take calculus, because then they'll never learn how to do the problem exactly, because these programs will do all those things.
They do everything for you.
Yeah,
yeah.
For you. So, which kind of brings up the question, well, then why should they learn to do it the hard way? I guess if the computer can do it for them, but
which is a
valid point, really.
You know, if you're a humanities major, that's probably a real good question.
Right. Yeah. So, but part of the reason, though, is that they learn how to be good problem solvers, for one thing. And the other thing is there's engineers in those classes, and, you know, the kind of people that are going to actually one day be telling the computer what to do. Yeah. And if you're going to have to tell the computer what to do, then you have to understand how it works before you can make it.
And you may be already doing this, but you just mentioned a word that struck home with me, because our students in hospitality sometimes are not the greatest problem solvers. Is that a tack that you could take, that you're not here to make you mathematicians, I'm here to make you problem solvers, and by learning the rigor of mathematics makes you a problem solver? Yeah,
that's a.
I mean, is that something?
That's a good way to actually. Back to the thing we were originally talking about. Yep. You're right. That's a good way to encourage them to.
Yeah. You're not here to learn math. You're
to be a problem solver. Yeah.
Problem solving, because the rest of your life, that's what you're going to. I mean, no matter what discipline you're in.
That's exactly right.
You're going to be a problem solver. So.
Exactly.
You know, how many dead ends do you have to go down before you hit the right answer?
Right.
And mathematics is probably a good teacher of that.
Yeah, I like that. I'm gonna try to drive that
just
home to them as well. Yeah.
You know.
Okay.
In your research.
Okay.
Give me a site.
Yeah, sure.
But problem solving is something we all have to do. No matter what we're doing.
Yeah.
And math might be a good, discipline for us to, at least understand, so that we can become better problem solvers.
Yeah. Well, there was a mathematician a long time ago that came up with some basic principles of problem solving. Yeah. And they're applicable, you're right, in every area.
This is how you approach it, this is how you break it down.
Exactly.
This is the steps you take.
Right.
And maybe that's something that, might work with
some of the people that don't like it. Yeah.
Well, yeah, because I'm thinking back to, I was not very attentive in math classes.
Okay.
Along the way.
Right.
And, once we got past percentages, I didn't know why I needed any of the rest of that stuff.
Okay.
Because I was never going to build a bridge, And
sure.
Until I got into engineering in the Army and had to build bridges.
Oh, you did?
Yeah, I was engineer officer candidate school, and had to build bridges. So.
Right.
All of a sudden I'm going, damn, I wish I paid
attention. I learned that. Yeah.
Would have been a hell of a lot easier if I'd paid attention. I knew where that timber was supposed to be to support the beams.
Right.
Yeah. But or even in I was a demolitions expert as well, and you had to learn how much to blow up an I-beam.
Okay.
How much C4 to put on the.
Right. Yeah. Yeah, that's definitely a mathematical problem.
Yeah, it was definitely.
Yeah.
Our formula was P equals plenty.
Okay.
Work out the formula and add another pound.
Okay. Right.
Make sure.
Yeah.
Because you want the whole thing to go down.
Definitely.
So.
Yeah.
But unless you're doing those kinds of things,
it reminded me. I read this article. I lived in Iowa for a while, and I read this article that they were going to try to knock down a corn tower.
Oh yeah,
it's basic, same idea as they put this dynamite around the bottom to blow it up, and the whole town actually gathered together to witness this event. They even had a raffle for the person that gets to, pull the button down, and so it was a big deal. And so this person pushed down the lever, and the explosives went off and out of the bottom, and the tower just went straight down. And stayed. Yeah. Didn't move anymore. Yeah. And they had a picture of it in the paper of this tower. It was 10 feet shorter, and
took out the bottom
right.
bottom 5 feet.
Exactly.
It just fell on itself.
Yeah. So you're right. put some thought into what you're doing before.
Yeah, you got to wrap it around the top as well, so the whole thing will crumble. And
you have experience with this, yeah.
Shh, don't tell
okay.
me. Former life.
Right.
But if you, I mean, they blow down buildings, and they get them to implode on themselves.
Right.
And it's all about where you plant the charges and how you plant them.
Exactly.
Everything, so you can actually bring a building down so it just falls on top of itself.
But it's good problem solving techniques that take you to that in the first place.
But that's all mathematics, I would think.
Yeah.
So how did a little kid from Colorado get all the way to England for a Ph.D. program?
That's a good question as well. My wife and I, we were both living in Colorado, and I was finishing my master's degree, and it was our first year of marriage, and we thought, well, I want to go somewhere else to do my Ph.D., and we figured if we have to move out of state, we might as well just move really far away. So, and we thought that was a good opportunity to really travel, and it was a great experience. I mean, we learned. You can never learn. I feel like you can't really learn about your own culture until you leave it.
True. Yeah.
So we learned so much. I mean, I learned a lot of math while I was there, but I learned a lot more than just that.
Now, is math different in England than it is in
their system of education is different, but math is the same everywhere you go. Yeah. There are different trends. I think actually there's a trend over there in the type of math that I did, and it's less pronounced in the U.S. than it was there. It's part of the reason I've ended up at Central Florida is because there's some other people in the department who do this same kind of thing, but it's hard to find in the rest of the U.S. Most of these people are in Europe, actually.
Why? So. What's the difference?
Well, so back to this, the thing about solving problems on computers.
Right.
That's what I did in my PhD. That was the field, and this idea. Maybe it started in Europe. I'm not really sure, but this idea is to somehow preserve the structure of the original problem. So when you try to solve it on a computer, like I said, you're doing an approximation,
right?
And you're going to destroy some of it somehow, no matter what you do when you put it on a computer to solve it. And so there are different ways to approach it, and one way is to say, well, let's preserve some part of it exactly, and then see what happens to the rest of the problem. When we solve it on a computer.
What you're saying.
Oh, you don't. So let me say for example. Here's a good example. They have if I want to predict where a satellite's going to be in its orbit, in say 100 years' time. Then I mean a long time.
Oh, so we're going out of
Then I would what I would do is I'd put in a computer this big system of equations that tells us how the solar system works and all this stuff. Because it's
what
really,
elliptical orbit?
Yeah, exactly.
Okay.
Exactly.
And how that elliptical orbit changes every time it goes around.
And the thing is with all the when you put all the satellites in there, you put the planets in there. It's a very hard problem to solve. Nobody knows how to do it. Well, that's the idea. That's why you want to solve it in the first place, because you don't want satellites colliding into other things, and it could be a mess, right? So that's why you care about this.
Okay.
So what they would do is put this in the computer and let it run for a while to see if predict where it's going to be in the future, and certain algorithms that you use, certain ways of solving it on the computer will tell you that the satellite's going to fly out of its orbit in 2 years' time, whereas it may not, because what's happening is as it continues to go in time, you're building up more and more error in your calculation on the computer.
It's kind of like trying to predict the path of a hurricane.
Right. It just the error builds. The more and more computations you do, the more error you get, and then you don't really know what's going on.
Okay.
So the idea with that problem is the problem is energy preserving. So basically the idea is that the Earth is going to stay in its orbit forever. It's never going to lose energy. It'll just always stay there. eventually it will fly out, but we assume it's energy preserving and it's going to stay there. And so we do that with this satellite. We say it's energy preserving. Okay, so let me ask you,
does the Earth's orbit around the sun, does that change every year? I mean, or is that a constant?
There are slight variations. Okay. This is not, it's a little out of my field, I guess. I'm not an
so the assumption the mathematicians are making is that it's going to stay constant.
Yeah, it's going to, you're right, it's going to come back to the same place it was. It's going to, and it's always going to stay in this
So you're assuming that constant, which is probably already building an error.
Well, that's not such a bad error to make, though, because it's been, you know, if you were to simulate it over 1 million years, it's going to stay, it's been there anyways, right? It's all